We are in Unit 6. This is our fourth section. We are going to be looking at separable differential equations today. Now, we've already solved a separable differential equation back when we solved our very first differential equation. So let me remind you, when we are asked to solve a differential equation or to find a solution to a differential equation. So a differential equation is any equation that has a derivative in it, like dy dx or f prime or whatever. So you're going to have some equation that has a derivative in it, okay? For right now, I'm just going to call it f prime of x, but I'm going to clarify that in a moment, okay? So it can be any equation that has a derivative in it. That's a differential equation, okay? When you're asked to solve or find the solution, you are finding the function. You're finding the function that meets this criteria for which this is true, okay? So solving a differential equation means finding the function, okay? And since this is a differential equation, we know that this function can have a constant in it, all right? You're going to be finding an equation that looks like that, all right? So you're finding the function, the y or the f of x or whatever, okay? This is called the general solution. This is the general solution because it has this plus c on it. Okay, this is a family of solutions. All right. Now, sometimes in the problem, they're going to give you information that allows you to find the value of c, and we did that back when we did a couple of solving differential equation problems that first time. So if they give you a point on this function, then you can plug in the point and solve for c, right? When you do that, when you get the actual, when that c becomes part of this function, whatever that is, then that is called the particular solution. It's no longer general, now it's particular, okay? So you'll see directions that say find the particular solution. And what that means is you're going to have to use the additional information to find that c value. And then this will be your particular solution. Okay? Now, there is an entire course devoted to solving differential equations in college. All right? In this course, we only solve one type of differential equation, and that differential equation is called, the type is called separable. Okay, separable. So let's take a look about, let's talk about what a separable differential equation looks like, okay? So, back when we first did this, we took a look at something maybe that looked like this. Dy dx is equal to x squared plus 1, where there were only x's over here, and that's fine. Another differential equation, though, we could have y over there as well, maybe x squared times y or something like that. So potentially you can have y's over here as well as x's. All right. Now, like I said, these differential equations can get super complicated. Ours are going to be pretty easy. All right. Well, relatively easy. But ours is the first type that's separable. So a separable differential equation, I'm going to abbreviate differential equation as diffEq. A separable differential equation can be written as some function with y's times dy is equal to some other function of x's times dx. All right? This is why it's called separable, because we can get all of our y's on one side multiplied by dy, and all of our x's on the other side multiplied by dx. It has to be multiplied by dx. Okay? So that is what a separable differential equation is. And of course, not everything can be gotten that way. And we're going to take a look at some of those too. All right? Once you get your differential equation in this form, then all you have to do is integrate both sides and solve for y. Okay? So, our mantra for solving a separable differential equation, our mantra is separate, then integrate. Integrate both sides. Separate, then integrate. Okay? All right, let's jump in and take a look at some examples. And now I'm going to go to your notes page. Hopefully everybody has a notes page. Hopefully either I gave it to you in class or you printed it off online. Okay, so let's go to our notes page. And a lot of that I just talked about is up here. I just hate just to read things to you. But anyway, there's our mantra right there. So let's take a look at this first example. Okay, our first example is this. We have, let me get a pen here. We have x squared plus 3y dy dx is equal to 0. I think my pen is running out of ink. Okay. So, we want to separate first of all, it is a differential equation because it has dy dx in it. All right. So, we need to separate and then integrate, right? So, one thing is important. You can only use math to separate it. You can't just snap your fingers and make things float to the other side that you want to the other side. For some reason, I have students who want to do that in this section. And when they're solving differential equations, they want to move things to the other side like as if they're doing it by magic. And it's not. You're using actual algebra here. Okay? So, I'm going to begin by moving this x squared over. When I move this over, what happens to it? I'm subtracting it on both sides, right? So I'm going to have 3y dy dx is equal to a negative x squared. You have no idea what I see kids do on this section, and I don't know why. All right? Anyway, that has to be a negative x squared over there. At this point, I need to move that dx over. So I'm going to multiply it on both sides. I'm going to multiply dx on both sides. So then I have 3y dy is equal to negative x squared dx, right? Okay. Do I have a function of y's times dy is equal to a function of x's times dx? Yes. And that's what we needed. We needed a function of y times dy is equal to a function of x times dx. Okay? So we separated. Now we integrate. Now, I will say this. That 3, do you agree that we could leave the 3 here, or we could move it to the other side and make it a negative 1/3 x squared dx? You could do that, all right? And that's perfectly fine. We're going to have to move it either now or after we integrate. But since we're going to be solving for y, we're going to have to move it at some point. So I actually like to go ahead and move it now, but I'm just going to leave it there for right now. Okay? So it is separated. Now we're going to integrate both sides. Separate, then integrate. All right. What's the integral of 3y dy? Well, that would be y squared times 3 over 2, right? Plus c, do you agree? Plus c. But what I'm going to do is I'm going to combine this c plus the c I get over here to another constant. So I'm not going to write the plus c here because I know I'm combining it with the plus c I'm going to get over there. Okay? The antiderivative here would be x cubed times negative 1/3, right? Plus c. So again, I'm combining the two constants into one constant. All right? Okay, so we separated, then we integrated, and now we just solve for y. Just solve for y. Now I will say this. Anytime after you integrate, we can plug in any initial condition that we're given to find c. We could plug that in now, or we could wait till after we solve for y, or we could do it on one of the in-between steps. It doesn't matter. I usually, at this point, I'll usually multiply by whatever I need to get rid of this coefficient. So I'm going to do that. I'm going to multiply both sides by 2/3, right? So if I multiply both sides by 2/3, I just have y squared on the left, and I have negative 2/9 x cubed, right? Plus 2/3 times c. Now I want you guys to think about that. What does c represent? C represents the constant of integration, right? C is just a constant. What do you get when you multiply 2/3 by some constant? Do you agree that that's another constant? Do you agree? I hope so, because it's very true. 2/3 times a constant is just another constant. So I can call this still c here. Are these the same c? No. Do we care? No, because it's just another constant. I did have a professor in class who liked every time c changed, we had to change the notation for c. Sometimes, where's my little scratch sheet? Sometimes we would call it c hat. Sometimes we would call it c bars. Sometimes we would call it c sub 1 or c sub 2 or whatever, c sub 3, c dot, c dot dot, you know. I had one professor who wanted us to do that, but most of them it's just another constant. Why are we haggling over the name of it? Just call it c. All right. However, if you wanted to, you could even keep it 2/3 c. However, it's going to make your math a little bit more complicated than it makes mine in a second. All right. At this point, I'm going to choose to go ahead and plug in my point. All right? I'm going to go ahead and plug in my point. So I'm plugging in the point. I need to communicate what I'm doing. So I'm going to say at 0, -4, comma, I have -4 squared is equal to -2/9 times 0 plus c. So what is c? Well, c is 16. Now I'm putting c value back in for my y equation. And just finish solving for y. What do we do on both sides here? We square root. And we're going to get plus or minus the square root of -2/9 x cubed plus 16. Okay? Now, I don't want to stop there, because when you solve a differential equation, you're going to get a particular, at a point, and we're given a point. When you're solving a differential equation and you're given a point, what is the answer going to be? What did I say the answer was just now? Gosh, I wish I hadn't put that away. Where did I put that? The answer, well, the answer is a function, right? The answer is a function. I know where it was. It's right underneath here. Okay. Anyway, the answer is a function. What did we get for our answer? We got two functions. Well, the answer to a differential equation is not two functions. It's one function, all right? So we need to narrow this down. We need to either choose the positive or the negative of this. How do you know which one to choose? Look at your point. That y value is -4, right? What's the only way to get a y value of a -4 right here? It's to ignore the positive and only keep the negative. Right? This is our answer. That is our particular solution. Okay? Number 2. Find the particular solution of this differential equation that passes through this point. Okay? I'm going to go to my other color here. It's nice and, this pen is nice and thick. All right. So differential equation, separate first. So I'm going to bring over dy dx is equal to -2xy. And we need to solve this differential equation, find the particular solution, so separate and then integrate. So let's separate. I need to get this y on the left-hand side. This is where kids start snapping their fingers and all of a sudden a y appears over here. What do you do to get the y over there? You divide both sides by y, correct? Which is the same thing as multiplying both sides by 1 over y. Yes? So we get 1 over y dy dx is equal to -2x. Now multiply both sides by dx. When we multiply both sides by dx, we get this. The -2 can either stay or be moved, right? But keep in mind, you're going to have to solve for y, right? So this, when we chose to keep the 3 here, we had to move it eventually. So I like to, if I have a number, I like to leave it on my x's side. All right? This is separated because we have a function of y's times what dy is equal to a function of x's times dx. Has to be multiplied. All right? So we separated, now we integrate. Okay, what is the integral of 1 over y dy? Natural log absolute value y. Antiderivative of -2x dx will be -x squared plus c. Okay, again, I'm combining those c's to make a different c. Okay, at this point, I take a look at my given point. I take a look at that given point because what would be a very convenient value of y in this? Natural log of what is very convenient? Either e or 1, right? So I take a look at that y value. If I get a natural log y, I take a look at the y value. If that was e or 1, I would go ahead and plug it in now. But it's not an e or a 1, it's a 5. So I'm not going to plug it in quite yet. I'm going to take, right here, I'm taking both sides of this equation, and I'm taking e to both sides. E to both sides. All right. Here, I'm going to have just the absolute value of y, right? On the other side, I'm going to come off to the side and think about this for a second. If I have e to the negative x squared plus c, which I do, that's what I have, e to the negative x squared plus c. I want to review a little bit of an exponent property. You guys, if you had x squared times x cubed, what is that? What's x squared times x cubed? That would be x to the fifth, correct? That would be x to the 2 plus 3, correct? So if I had 2 to the x times 2 to the y, that would be 2 to the x plus y, correct? That's a property of exponents. So what do we have? We have e to the negative x squared plus c. That is equal to, if I go backwards, that is equal to e to the negative x squared times e to the c, correct? So I'm going to write that here. E to the negative x squared times e to the c. So I'm changing that. You'll see why in just a second, all right? Now, this e to the c. E to the c. C is a constant, so what is e to the c power? Just another constant. This is just another constant. So I'm going to call that c for a constant, and I'm going to pull it out in front. So I have the absolute value of y is equal to c e to the negative x squared. Okay? Now let's take a look at this. I want to examine this absolute value of y. Doesn't the absolute value of y is equal to this mean that y can be the positive or a negative of this? Right? And doesn't that depend on the value of c? So we can ignore the absolute value and let the c absorb that, because we're going to have to find the particular solution, right? So we're letting that c absorb the positive or negativeness of it. Essentially, we're multiplying by either a positive or negative, and we get another constant. So when you are at this point right here, and you e to both sides, I would love for you to be able to go directly to there. Okay? So e to both sides, you get y is equal to c e to the negative x squared. Alright? But this is y. Alright, now I'd like to find c. Now is a fine spot to go and find c. So I'm at the point 0, 5. We have 5 is equal to c e to the 0. What is e to the 0? E to the 0 is 1. So this gives us c is 5. So our solution, our particular solution, is y is equal to 5 e to negative x squared. That's our particular solution. And I just boxed that, but you don't need to box that. Okay. Alright, let's look at another example. For your example 3, we have this differential equation to solve. So I'm going to begin by separating. Let me write this down again. So we separate. So how do we move? I want to leave the 2. Well, we can take the 2. We either take the 2 with you or leave it there. It doesn't matter. If we do move the 2y, we're going to be multiplying both sides by 2y, right? Multiply by 2y. Okay, no, you don't have to show that. I'm showing that again because for some reason kids just like move it and keep it in the bottom here, and or they add it, or I don't know, they do weird things to get it over there. we're multiplying both sides by 2y. And then we're going to multiply both sides by dx, right? Let's go ahead and multiply both sides by dx. So we get 2y dy is equal to negative sine x dx. Right? So separate, but take, don't rush into that. Just take your time and do it correctly. Now we have a function of y times dy is equal to a function of x times dx. Time to integrate. Okay, the antiderivative, this is one of the reasons why I took the 2 with me, because the antiderivative of 2y is just y squared plus c, which I'm going to add to the other, I'm going to subtract from the other c over here, okay, is equal to the antiderivative of negative sine is positive cosine x plus c. All right? So at this point, any time after you integrate, you can go ahead and plug in your point to find c, right? Sometimes it's good to do it right away. I usually, after I integrate, I'll look at the point and I'll say, okay, is this a good time? Or do I want to wait? And I think this is as good a time as any. If I continue and solve for y, I'd be taking the square root of both sides, and I'm not sure if I want to solve that for c. So I think this is as good a time as any to plug in that point. So I'm plugging in, so I'm saying at the point pi over 3, 2, I have 2 squared is equal to cosine of pi over 3. What's cosine of pi over 3? A half plus c. Okay? Subtract a half from both sides and we'll get the value of c. 4 is 8 halves, and 8 halves minus 1 half is 7 halves. So c is 7 halves. So our equation becomes this. And now just solve it for y. So y, if we square root both sides, we'll get plus or minus. Y is equal to plus or minus the square root of cosine x plus 7 halves. Now, 2 answers here. We only want one answer. So what is y? We look at the sign of that y to tell us which sign to keep here. So y will just be the positive square root of cosine x plus 7 halves. All right? So if you want to, spend a moment writing down why we only kept the positive and not the negative. We looked at the sign of that point. All right? Number 4. Solve this differential equation. So we have e to the x minus e to the y dy dx is equal to 0. Okay? Well, separate and integrate. So to move the e to the x, I'm going to subtract it on both sides, right? Since they're both negative, I'm going to multiply both sides by a -1 in my next step. And I'm also going to multiply both sides by that by dx, right? So I'm going to have e to the y dy is equal to e to the x dx. Function of y times dy. Function of x times dx. Time to integrate. The antiderivative of e to the y is e to the y plus c. That plus c I'm adding to the other c. The antiderivative of e to the x is e to the x plus c. Okay? Again, I just integrated, so I automatically look at that point and I ask myself, is this a good time to plug it in? And I see what will happen if I plug in the 0.11, and so it's, yes, it's a good time. At the 0.11, I'll have e to the 1 is equal to e to the 1 plus c. That's e is equal to e plus c, so c has to be 0. So I get e to the y is equal to e to the x, and now I need to solve that for y. Well, how do we solve that for y? We take the natural log of both sides, right? And we're going to get y is equal to x. Nice. Okay, so that's our particular solution to the differential equation, and our solution goes through that point. You can always check it again, plug that point back in, make sure it's true. Okay, number 5. Find the particular solution of this differential equation given that this point is on the solution curve. Well, this doesn't look like a differential equation, but it is because it has a derivative in it. I'm going to choose to rename y prime dy dx just for our purposes. I really don't know that x is my independent variable here because there's no x's in the problem. It might be t's, it might be u's, it might be v's. You can name it anything you want, but I'm very used to x's, so I'm going to call it dy dx is equal to 3y plus 6. Okay, here is where kids start to do funky things with what they bring over, how they separate this. I say, okay, how do we get all of our y's over here? How do we get all of our y's over here? And usually in class, I'll have a student say, subtract it over. Well, if I subtract it over, I get this. If I just subtract it over, that's what I get. Already I can see I'm in trouble because I have a plus dy instead of a times dy. And how do you move the dx over? Wouldn't you have to multiply both sides by dx? So then we would have negative 3y dx plus dy is equal to 6 dx. That is not separated, right? So then you're like, okay, maybe how do we get rid of just that dx? Well, you can't. You can't just get rid of that dx. So let's go back to our original problem here. And again, ask yourself, what do you do here? How do you get a function of y times dy is equal to just dx? Well, I'm going to begin by multiplying both sides by dx. So multiply both sides by dx. Now what? We have a choice. Divide both sides by that 3y plus 6. Divide both sides by that. Or factor out a 3 and just divide both sides by y plus 2 and leave the 3. Either one will be fine. Either one will be fine. I like this way better because this, when we integrate, this will just give me natural log of y plus 2. I won't have to multiply by anything. If we integrate this, we'll have natural log of the 3y plus 6, but then I'm going to need a 1/3 multiplied by that. Okay? So either way is fine. I like to factor out what I can from this before I divide. So that's what I'm going to do here. So I am multiplying both sides by the dx, and I'm going to go ahead and factor out a 3. Now I'm going to divide both sides by y plus 2. Function of y times dy is equal to a function of x times dx. A constant can be considered a function of x or y, right? So either one. It is separated, so now we integrate. The integral of 1 over y, the derivative, if we think of this as a u sub, the derivative of u here would just be a 1, right? So this is just the same as ln y plus 2, absolute value y plus 2. And this is equal to the antiderivative of 3 dx, so 3x. Here again, I'm taking a quick look at my point because remember ln of e is nice and ln of 1 is nice. So if my y value in this point was a -1, I would go ahead and plug it in now. It's not though. So instead of plugging it in now, oh, I forgot my plus c. Do not forget your plus c. Goodness. So instead of plugging in the point right now, I'm going to do a little work on this. So I'm going to e to both sides, right? So this will be y plus 2. Remember that we can lose our absolute values because our constant will absorb that, is equal to c e to the 3x. And you can go back and refresh yourself on why that's true, but that's true because of one of the properties of exponents and the fact that e to the c is just another constant. And remember, we can lose the absolute values because whatever the value of c is, that will take care of the sign of our answer. Now it's a great time to plug in. So at the point 0.07, we'll have 9 is equal to c e to the 0, so c is 9. Y plus 2 is 9 e to the 3x, so y is equal to 9 e to the 3x minus 2. Particular solution. Example 6. Let's find the particular solution of this differential equation. Don't get all fixated on x's and y's. So in this one it's b's and t's, and we have to use b's and t's, all right? So we have db dt is equal to 15 minus b. Okay? We have to separate. So again, I'm going to begin by multiplying both sides by the dt. And now I'm going to divide both sides by 15 minus b. There's nothing to factor out and leave, so I'm just going to, I could factor out a -1. Actually, I could factor out a -1. But I don't know that you would do that. So I'm just going to leave it in there like this. Okay? This is separated. Function of b times db, function of t, 1, times dt. So time to integrate. Alright, what is the integral of that left-hand side? What's the antiderivative? Here's my thought process. If I let that be a u prime will be a -1. So this is a natural log. If you take the derivative of that bottom and there's still a variable in it, it is not a natural log, okay? But if you take the derivative of the bottom and then you get just a constant, it is a natural log. So this is a natural log, but the derivative is a -1, not a 1. If the derivative is anything other than 1, you have to undo it. So I have to multiply by a negative out here to undo that in the derivative. That's doing a u sub in our heads, all right? On the right-hand side, the antiderivative of dt is just t plus c. Okay? I'm taking a look at well, I would probably go ahead and multiply by a -1. So I'm multiplying both sides by a -1. Multiplying by a -1. Okay, so I have natural log of that is -t plus c still, right? Because a -1 times a constant is just another constant. Okay? Now I'm taking a look at my point. The b value is a 2. That does not give me a pleasant natural log, so I'm just going to go ahead and e to both sides. E to both sides. I can lose my absolute values and let the c absorb that sign. Okay? Now we plug in the point. So at the point 0, 2, we'll have 13 is equal to c e to the 0. So c is 13. So 15 minus b is 13e to the -t. Solve for b. b is 15 minus 13e to the -t. Particular solution. Number 7. Find the particular solution of, that should be an f, of this differential equation. Okay, take a look at it. How do we separate it? You'll probably tell me to subtract y on both sides. That can be a problem to subtract, like we found out in this other example. If you try to subtract the y, it's going to be hard to get that y times dx, right? Because you would have this. And then when you try to multiply both sides by dx, you're going to have a dx here and dx there. Not a good approach. So not a good approach. This is an example of a non-separable differential equation. This is not separable. You can't do it. So we cannot solve this in this course. You have to wait until you get to differential equations in college. Okay? Got to use a different technique. All right. I will say this. Differential equations, solving differential equations on the AP exam are always worth a lot of points. Let me quickly give you a breakdown of points that you would score on this, okay? You always get a point just for separating. So just separating, you get a point. Okay? Then you usually get another point for your antiderivatives. Well, just your antiderivatives. Okay? Then you get a point for using the initial condition to find C. Okay? So using that initial condition and finding C gets you another point. Sometimes they even split that out. And they give you a point just for having plus C in here, and then for finding C using the initial condition. So 1 or 2 points for that. And then another point usually for solving for Y. That's a lot of points for an FRQ. An entire FRQ is only worth 9 points. So if one part gets you 4 or 5 points, that's huge. That is huge. So you really do need to know how to solve a differential equation. Okay? All right, so your turn to practice.